Hi, it's Alex again. This is going to conclude the computer vision part of the crash course. Obviously, it's impossible to really go into a lot of detail there, so I'm really just going to give you a bit of an appetizer of what actually can be done in computer vision, and I strongly encourage you to dive more deeply into the various computer vision toolboxes and the various chapters in order to get deeper insight. So we're going to look at object detection, just overall what you can do beyond just image classification. In short, here's the problem. Suppose I have a picture of a dog, then building a classifier like in ImageNet which says dog or fridge or cat or cow or I don't know, maybe basketball is relatively straightforward. All the images have kind of the same size and then you just go and convolve. Now imagine I give you a picture of those three animals, like a dog and another dog and a cat, then classifying this image as cat or dog is both wrong, right? Because there are more animals on it. So the correct thing would be to actually segment this out and say, well, hey, there are two dogs in this image and one cat, and here's where they are. And maybe even give the boundaries. Now, why does this matter? Well, suppose I want to build a self-driving car, then it's a really good idea if I have some idea of where the cars are and what else is there. So for instance, recognizing that there's a human riding a bicycle is a really good idea because I can then predict how this human is going to drive more slowly and whatever. Okay. So especially in San Francisco, this is important for survival. Now, let's actually look at that in a bit more detail. So these are some demos from Gluon CV, and they're all easily downloadable, so you can try it out. And this is an example of, a street and a couple of cars standing there, and here are people running around, and you can see how it nicely, puts boundary boxes on it, and it seems to be particularly obsessed about handbags. But overall, it detects people very nicely. And then, here there are cars, and this is, somewhere in, in Spain, I suppose, and it recognizes, where the cars are, traffic lights and other things. And it doesn't just go and give you where the cars are, but also the outline. And here it does semantic segmentation, so we get humans and street and trees, and here are some humans that are not looking when the cars are driving, but that's okay because it's a pedestrian zone. This is probably somewhere in Germany, given that it's a Mercedes-Benz and it says WC, in other words, toilet there. In any case, so there's segmentation. Again, you need that. Pose estimation, you might need that for motion capture and so on, especially if you're doing things in movies and animation. So suppose you wanted to replace this beautifully dancing couple with a couple of Shrek animations. Well, that would be a lot easier if you can just do proper motion capture to begin with. And yeah, sometimes your images get a little bit less good because the camera resolution decreases, or maybe the camera gets dirty or whatever, and you still want to be able to recognize this. So this is probably also somewhere in Silicon Valley suburbia. Yep, it's Highway 101. Anyway, so this is what you can do with video analysis. With basically, you would probably want to do some meaningful low-pass filtering there. So in short, what this does is it allows you to detect nicely where objects are and how they're moving and what their boundaries are and so on. So obviously this is more than what I can cover in a crash course, and it would easily be the content of an entire summer school of its own. So all I can do is give you a few ideas. First thing that you care about in computer vision is what's called a bounding box. So bounding boxes are either, just the coordinates or just, the reference point and then the height and the width. And there are nice data sets, for instance, COCO. So common objects in context contains 80 object types, 330,000 images, and a total of 1.5 million objects. In other words, there are probably about 5 objects per image on average. And yeah, the icons below tell you kinds of objects it recognizes. So for some reason, giraffes are really important. Cows also, but polar bears not so much. Anyway, so you can argue about whether that's the right set of categories, but that's what they picked. So what you basically do is then a detection algorithm would go and propose multiple possible regions, and then within those regions that are also called anchor boxes, then try to find out whether an object's in there and where it is relative to that anchor box. So the problem is basically if I give you an image of an arbitrary size, how do I detect where things are? Well, I first go and essentially break it down into smaller pieces, and then I try to see whether I can find the object in the smaller piece. And then I zoom out, and as I zoom out, I will thus get objects of larger size as well. So in short, those anchor boxes really make the problem somewhat more translation invariant. And while objects can overlap, I can also use the fact that, well, something cannot be simultaneously a cat and a dog. Well, that basically I have some what's called non-maximum suppression. In other words, I use the strongest signal as the thing to decode. There are better ways how to decode things, but that's a decent way to start. So for instance, you might actually want to use something like a transformer decoder. And if that hasn't been done yet, well, then go forth and write that paper. IOU, intersection of a union. So it's basically just a fancy different way of referring to the Jacquard index, because if you call it the Jacquard index, you cannot write the paper about using that new measure. In other words, it's really just the intersection between where you think the cat is and where the cat actually is, divided by the union over the both sets. And obviously, this gets worse if I just pick a really large union. So in other words, if my proposal region is really bad, because if my proposal region is really large, then the intersection, of course, is going to be identical to where the cat actually is, but then the proposal is so bad that it becomes meaningless. Likewise, if I miss the cat, even if I do it very precisely, it's still bad. So this is the nice thing about the Jacquard index, that it captures those two pathological cases. Then what you go is you use each anchor box as a training example, as in, does it contain a cat, does it not contain a cat? And then you label this anchor box with, does it contain anything interesting or not? And if so, where is it? This gives you lots of negative examples because most of the segments are empty. So for instance, if you have a large portion of the sky, then usually there's nothing in the sky. Maybe occasionally there's a plane, but mostly there's nothing. One way of addressing this is what's called non-maximum suppression. So where you basically go and say, out of the possible candidates that are overlapping, the one that's the most confident wins, and you remove all the other candidates and you keep on iterating. So this sounds really complicated, but here's a caricature of it. So in this case, we're actually assuming that all the bounding boxes overlap, and so there can only be one within each anchor box. That's a little bit of a caricature, but I think you get the idea. So you might have, the highest score for bounding box 3 within the anchor box 2. Okay, so therefore nothing else can be in the anchor box 2, but there can also be no other bounding box 3. Okay, so then we go and eliminate this. So we've already picked something there. Then we find that the next highest score is in row 7 and column 1. So we eliminate this, and then we play this game again, and now we find something in column 4 and row 5. And so in doing so, I get an effective algorithm for scanning over possible proposals and only picking the one that's really the most relevant one. Okay, so now armed with this, we can look at different ways how to actually detect objects. And the simplest way is to simply go and, scan over the image. And whenever I find something interesting, I run that through a convolutional neural network and I predict the bounding box and the category. And maybe I use some heuristic to actually find those candidates, and then I'm done. The problem with this is it's ridiculously expensive because you need to run a convnet whenever you think something might be interesting, and it's not a very nicely integrated end-to-end approach. One of the problems though is that those regions have variable size, you may end up cropping and whatever, so we need to have a device that goes and chops this back into the right size. And this is exactly what ROI, region of interest pooling, does. And ROI pooling simply goes over a larger object and then it pools over the largest terms, and it just takes the entire anchor box regardless of its aspect ratio and cuts it into n by n blocks and then returns the maximum value for each block. So in doing so, we make sure that no matter the original, we get an n by m set of values out of it. It's very ham-fisted, but it works quite well. And so if I do that, then I don't necessarily need to invoke a CNN for every single patch that I heuristically select, but I can just apply this to the entire image and I perform this pooling. Then I use some dense layers and I'm done, right? So the benefit of this is it's a lot more computationally efficient, and that's actually why it's called the fast region CNN as opposed to just RCNN. Now, things wouldn't be great if this was already the end of progress. So after the fast RCNN, what are you going to call the next paper? You're going to call it the faster RCNN. Now, in this case, rather than using a heuristic, you use something that's trained. And so you use a region proposal network to come up with some ideas for an anchor box, and then you do that instead of whatever heuristic you had. And that turns out to be faster. So that's why it's called the faster RCNN. Now, of course, you can do even better. If you have information not just about the image, but also where the objects are, how they are segmented, and then you can identify them. So this is what can be done with mask RCNN, where you basically have, in addition to everything else, a mask prediction problem through what's called a fully convolutional neural network. In other words, you just run your convnet at the full resolution. This is very expensive, and there are some tricks on how to address this by playing with variable resolutions in the middle. But suffice it to say, mask RCNN and variants of that give you exactly where the objects are, what they are, whether they are distinct, and what the outlines are. This gives you very, very high accuracy, albeit very slow. So on this specific device, for instance, this was running at maybe 2 or 3 samples per second. That's quite terrible, but it's very accurate. Now, so the x-axis is samples per second, the y-axis is the mean average precision, and you want to be up here, but you also want to be out there. So now how do we make it faster? After all, we haven't explained those green lines yet. Let's see. So there's something called a single shot multi-box detector. So the idea is essentially you just come up with a couple of regions right away. So you have maybe different sizes and you have different aspect ratios. And so rather than taking the product of number of sizes times number of aspect ratios, you pick a generic size, and for that you try all the aspect ratios, And then you pick a generic aspect ratio and you try out all the different sizes. So you get n plus n minus 1. And of course, you can vary that to make it mildly depend on both numbers. You can do tricks there. In any case, what you do is you basically have your base network, and then you predict the anchor boxes, and you rescale things, and you predict the anchor boxes again. And you do that from fine to coarse, because you do that at the high resolution first, and then you downres it. And so this way, you get predictions for classes and bounding boxes for each of the anchor boxes, and this works okay. So with okay, it means it's fast, but not very accurate. And so then this network came along called YOLO, and there are like now versions 2 and 3 and 4. And 4 is mostly re-implementation, but they called it version 4, which didn't exactly excite the authors of versions 2 and 3. Regardless, basically what you do is you just, in a very brute force manner, shred the image into non-overlapping boxes. And you just try to predict for every box what's there. And this works surprisingly well. So you can see fairly high accuracy, actually pretty much as high accuracy as a simple version of a faster RCNN, but at much higher throughput by a factor of maybe 20 or 30 faster. So, of course, what I showed you right now is no substitute whatsoever for a proper computer vision course. And that would be an interesting class to be teaching on its own. But what I hope it did is it gave you a little bit of an idea of, how to actually deal with multiple objects in an image, how to detect and identify them, that in some cases you may want to segment. And then ultimately a lot of the engineering that's going into those problems is how to cleverly and, not in a non-redundant manner, propose regions in such a way that you don't waste a lot of computation. There are a lot of book chapters that go with this, about 6 of them at the very least, but I would recommend that you really peruse the entire computer vision chapter. Okay, some people might say it's not really computer vision, it's basically deep networks on 2-dimensional images with 3 channels, and maybe there's some point to it, but regardless, enjoy this, and this might get you started on how to do some more meaningful computer vision.